In order to determine the energy density of an electrostatic field in a dielectric material, we start with the simple example of a charged parallel plate capacitor with dielectric. Let us consider a parallel plate capacitor with a homogeneous and isotropic insulating material of relative permittivity epsilon or that completely fills the space between its plates. Here A denotes the area of each plate and D is the distance between the two plates. Then the volume V of the dielectric medium between the plates is given by the product of the area A and the distance D. If the plates have the opposite charges plus and minus Q, then the electric field E is uniform between the plates. When we derived the capacitance C of a parallel plate capacitor, we found that it is equal to the vacuum permittivity epsilon naught times the relative permittivity epsilon R of the dielectric between the plates, times the area A of each plate over the distance D between the plates. By definition, the proportionality constant C describes the relationship between the charge Q on the plates of the capacitor and the voltage Vc through the capacitor, that is the potential difference between the plates. We already saw that the energy U of a charged parallel plate capacitor is given by 1/2 times the capacitance C of the capacitor times the square of the potential difference Vc between its plates. For the uniform electric field E between the plates of the capacitor, the voltage Vc can be written as the magnitude of the electric field strength E times the distance D between the plates. If we substitute this relation together with the expression for the capacitance C into the right-hand side of the equation, then we obtain 1/2 times epsilon naught times epsilon R, times the volume V of the space between the plates, times the square of the magnitude of the electric field strength E. Since the energy density U of the uniform electric field within the volume V is simply the energy U divided by the volume, we obtain 1/2 times epsilon naught times epsilon R, times E squared. In the right-hand side of this equation we can recognize the magnitude of the electric displacement D in the dielectric given by epsilon naught times epsilon R times the magnitude of the electric field strength E. Then the energy density U is simply equal to 1/2 times the product of the magnitudes of the electric field strength E and the displacement D in the insulating material between the plates of the capacitor. We can also express U in terms of the magnitude of the displacement D, stating that it is equal to 1/2 times D squared over the product of epsilon naught and epsilon R. Because the electric field strength E and the displacement field D have the same direction in an isotropic medium, the dot product of these vectors is given by the product of their magnitudes. Then the energy density U in an isotropic dielectric can be written as 1/2 times the dot product of the electric field strength E and the displacement vector D at any point in the medium. In fact, the displacement field D is defined by the sum of the vacuum permittivity epsilon naught times the electric field strength E and the polarization field P in the dielectric. If we insert this definition into the dot product in the energy density U, then we can express the later as 1/2 times the vacuum permittivity epsilon naught times the square of the magnitude of the electric field strength E, plus 1/2 times the dot product of the electric field strength E and the polarization P. Here we see that the energy density of a charged capacitor has contribution from two terms which we interpret as follows. In the term 1/2 times epsilon naught times E squared we recognize the energy density U naught of the electric field E in a vacuum. Then the energy density U of the capacitor can be written as the sum of the energy density U naught and another term UP related to the polarization of the medium between the charged plates of the capacitor. Indeed, the energy density UP, that is the difference between the energy density U of the capacitor and the energy density U naught, is given by 1/2 times the dot product of the electric field strength E and the polarization P. For a linear and isotropic medium the polarization vector P is equal to epsilon naught times epsilon or minus 1 times the electric field strength E. Then the energy density UP is equal to 1/epsilon naught times epsilon or minus 1 times E squared, depending on both the magnitude of the electric field between the plates and the relative dielectric constant epsilon R of the medium between the plates. We will show that the energy density UP defined here is simply the energy required to polarize a dielectric material per unit volume. Firstly, we recall that the polarization of a dielectric occurs when the electric field causes the charges within its molecules to become displaced. Then we assume that the charge distribution in the molecules enclosed by a volume V of the insulating material can be described by the position vectors Ri of a system of n-point charges Qi within the molecules with respect to an arbitrary point O. When an external electric field E acts on the molecules within the volume V, the electric charges in the molecules change their positions due to either induced polarization where opposite charges are displaced in or opposite to the direction of the field, or orientation polarization where the charges change their positions as the polar molecules change their orientations in the field. In both cases, the infinitesimal displacement of these charges can be described by the differential of the position vector Ri of each point charge Qi. The infinitesimal work dWi required to move the point charge Qi through the infinitesimal distance described by the vector dRi, is given by the dot product of the force Fi of the external electric field E acting on the point charge and the displacement vector dRi. By definition, the electrostatic force Fi acting on the point charge Qi is equal to the charge Qi times the electric field strength E, and the infinitesimal work done on the point charge can be written as Qi times the dot product of the field strength and the vector of the infinitesimal displacement of the point charge. Then dW, denoting the infinitesimal work per unit volume done by the external electric field E to produce the infinitesimal displacements dRi for all the point charges Qi, is equal to 1 over the volume V enclosing the molecules, times the sum of the infinitesimal work dWi from I equals 1 to n for each point charge within the volume V. Hence, the infinitesimal work per unit volume is given by 1 over V, times the sum of Qi times the dot product of the vectors E and dRi from I equals 1 to n. Because the external field E is uniform in space, we can write the right-hand side as the dot product of the field strength E and the differential of a quantity given by 1 over the volume V, times the sum of the charge Qi times the position vector Ri of the point charge Qi from I equals 1 to n. Here the product of the charge Qi times the position vector Ri of the point charge Qi gives the electric dipole moment Pi of the point charge, and its sum averaged over the volume V gives the approximation of the polarization field P in that volume. As a result, the infinitesimal work per unit volume denoted by dW is equal to the dot product of the electric field strength E and the differential of the polarization vector P. If we apply the formula stating that the polarization P is given by the vacuum permittivity epsilon naught times the electric susceptibility chi E of the linear dielectric slab between the plates of the capacitor, then the right-hand side of the equation can be written as epsilon naught times chi E times the dot product of the vector E and the differential of the vector E. This expression is also equal to the differential of 1 over 2 times epsilon naught times chi E times the square of the magnitude of the vector E, where E squared is simply equal to the dot product of the vector E with itself. By substituting the polarization P back into this equation, we can write the infinitesimal work per unit volume as the differential of 1 over 2 times the dot product of the vectors E and P. If we compare this result with the definition of the energy density UP, we can see that the latter is equal to dW, that is the infinitesimal work per unit volume. If we integrate this expression, then obtain the work W required to polarize the dielectric per unit volume, which is equal to 1 over 2 times the dot product of the field strength E and the polarization P. Then we prove that this work per unit volume is equal to the energy density UP defined by the difference between the total energy density of the charged capacitor and the energy density of the electric field produced by the free charges on its plates. We note that the differential of the work per unit volume presented here is frequently written in an integral form, where one determines the work W per unit volume done to change the polarization of a dielectric from 0 to a value P in an external electric field E. Then W is equal to the integral of the field strength E with respect to the polarization P' from 0 to the vector P. In order to calculate the integral, we need to express the electric field E in terms of the polarization P, like the linear relation between the vectors P and E with the coefficients epsilon naught times chi E used here to manipulate the differential form of W. If we expand these vectors in a Cartesian coordinate system attached to the insulating medium, then the integral of the vector E with respect to the vector P' is equal to the sum of the integrals of the component I of the vector E with respect to the component I of the vector P' from 0 to the component I of the vector P, where the index I runs through the Cartesian coordinates x, y, and z. We have shown here that the integration for a linear dielectric in a uniform electric field gives 1 over 2 times the dot product of the vectors E and P, but the question arises whether the energy density or the work per unit volume can still be written in a simple form in a more general case. Now we generalize this case and consider a problem, where we determine the energy density in a polarized and homogeneous dielectric under the influence of a non-uniform external electric field. This means that the electric field strength E and the displacement field D describing the net electric field in the insulating material depend on the position in the medium. So is the relative permittivity of the linear but inhomogeneous dielectric material in the equation stating that the displacement D is equal to the vacuum permittivity epsilon naught times the relative permittivity epsilon or times the field strength E. In order to determine the potential energy in such a case, we start with the first Maxwell equation in electrostatics telling us that the divergence of the displacement field D is equal to the free electric charge density ρ. We also recall that the total potential energy U of the charge distribution ρ is given by 1 over 2 times the volume integral of the product of the charge density ρ and the electrostatic potential phi over the whole space where the scalar fields ρ and phi do not vanish. Now we apply the variation of the Maxwell equation, which states that the divergence of the variation delta d of the displacement is equal to the variation delta ρ of the density of the free charges. Similarly, we can write the variation delta U of the potential energy as 1 over 2 times the volume integral of the variation of the product of ρ and phi. Here we use the fact that the variation operator delta acting on a vector field and the nabla operator acting on that field commute, which also true for the operator delta and the volume integration applied on scalar fields. For the variation of the product of ρ and phi in the volume integral describing the variation of the potential energy, we can apply the product rule for variation and we obtain phi times delta ρ, plus ρ times delta phi in the integrand. We already saw that the electrostatic potential phi at the position are produced by an electric charge distribution ρ can be written as 1 over 4 pi times epsilon naught, times the volume integral of the charge density ρ at the position r prime over the magnitude of the difference between the position vectors r and r prime, where the prime applied on the volume element of the integration indicates that the position vector r prime points to the position of the volume element. The variation of the potential phi gives a formula where the variation of the electric charge density ρ will appear in the integrand of the volume integral. We can substitute this expression into the volume integral of ρ times delta phi and exchange the order of integrations. Then we can exchange ρ evaluated at the position r with delta ρ evaluated at the position r prime as well. As a result, the inner integral gives the potential phi evaluated the position r prime and we obtain the product of delta phi and ρ in the integrand. Since all the quantities are primed in the integral, we can drop the prime and substitute this result into the variation of the potential energy U, and the later can be written as the volume integral of the product of the potential phi and the variation of the charge density ρ. Now we apply the variation of the Maxwell equation in the volume integral describing the variation of the potential energy U, and replace the variation of the charge density ρ by the divergence of the variation of the displacement field d. By using the product rule for the nabla operator, the product in the integrand can be written as the divergence of the product of phi and delta d, minus the dot product of the gradient of phi and the vector delta d. Here we split the integral of the difference into two integrals and apply the divergence theorem for the first term, converting it into a surface integral of phi times d over an arbitrary boundary surface enclosing the domain where the potential and the displacement field do not vanish. If the boundary is at infinity, then the boundary integral vanishes as the integrand falls off faster than 1 over the square of the distance measured from the localized charge distribution in the dielectric medium. Hence, the variation of the potential energy U is equal to the volume integral of the dot product of the negative gradient of the potential phi, and the variation of the displacement field d. By definition, the negative gradient of the electrostatic potential phi is equal to the electric field strength E, which can be substituted into the volume integral and the integrand becomes the dot product of the vectors E and delta d. At the same time, the variation of the potential energy U can also be expressed as the volume integral of the variation of the energy density U of the electrostatic field. By comparing the two forms of the variation of the potential energy U, we can state that the variation of the energy density U is equal to the dot product of the electric field strength E and the variation of the displacement vector d. Because the variation operator involves only an infinitesimal change in the physical fields, this equation can be reformulated in the form where the differential of the energy density U is given by the dot product of the electric field strength E and the differential of the displacement vector d. In order to obtain the energy density U itself, we need to integrate this equation as we did in the case of the work per unit volume done to polarize a dielectric. Then the energy density required to change the electric displacement in the dielectric from 0 to the value d is equal to the integral of the electric field strength E with respect to the displacement vector d prime from 0 to the vector d. We already saw that such a type of integral can be calculated in a Cartesian coordinate system attached to the insulating medium. Then the energy density U can be written as the sum of the integral of the component I of the field strength E with respect to the component I of the displacement d prime from 0 to the component I of the displacement d, where the index I denotes the Cartesian coordinates x, y, and z. Here the component I of the displacement d is equal to the absolute permittivity epsilon of the dielectric times the component I of the field strength E, where epsilon is equal to epsilon naught times epsilon r. If we substitute this expression into the integrand, then we need to integrate 1 over epsilon times the component I of the vector d prime with respect to d prime. Here we could factor 1 over epsilon out from the integral even if epsilon depends on the position in the insulating material. That can be done since permittivity is a property of the material whereas d' is an independent quantity describing the electric field in the material. The primitive function of the integral is simply equal to the square of d' I over 2 which is evaluated at 0 and di. As a result, the energy density U is given by 1 over epsilon, times the sum of the square of the component I of the displacement d over 2 for the index I equals x, y, and z. Now we can apply the formula expressing the components of the vector d in terms of the components of the vector e, and write the right-hand side of the equation as 1 over 2, times the sum of the component I of the vector e times the component I of the vector d for the index I running through x, y, and z. Now we conclude that under the influence of a non-uniform external electric field the energy density U of a polarized and homogeneous material is equal to 1 over 2, times the dot product of the electric field strength E and the displacement vector d, where both the energy density U and the vectors E and d depend on the position. This formula shows that we can generalize the expression derived for uniform external electric field and homogeneous dielectric to the cases involving non-uniform electric fields and inhomogeneous insulating materials. By inserting the definition of the electric displacement vector into the formula obtained here, we can see that the expression 1 over 2 times the dot product of the field strength and the polarization vector derived for the work done to polarize a dielectric in a unit volume also holds in more general cases. Now we determine the change in the energy of a charged parallel plate capacitor with a vacuum or air between its plates when a dielectric slab is inserted between its plates that fills the whole space there. As we did in the analysis on the change in the capacitance of the capacitor in such an experiment, we consider two cases here. When the electric charge stored on the plates of the capacitor is constant, and when the voltage or the potential difference between its plates is constant. Let us start with the setup where the amount of charge is stored on the plates of the capacitor does not change during the experiment. We already saw that the potential energy U0 of the capacitor with a vacuum or air between its plates is equal to 1 over 2, times the capacitance C0 of the capacitor times the square of the voltage V0 between its plates. Here the capacitance C0 depends only on the geometry and the size of the capacitor. We also saw that if we insert a slab made of a dielectric material between the plates of the charged capacitor, then both the capacitance of the capacitor and the voltage through the capacitor will change. It was shown that for a slab filling the whole space between the plates the capacitance C of the capacitor is given by the relative permittivity epsilon naught of the dielectric times the capacitance C0. Similarly, the voltage V through the capacitor is equal to the voltage V0 over the relative permittivity epsilon naught. In this case the potential energy U of the capacitor can be written as 1 over 2, times the capacitance C of the capacitor times the square of the voltage V between its plates. If we substitute the expressions for the capacitance C and the voltage V into the right-hand side of this equation, then we obtain 1 over 2, times C0 times V0 squared over epsilon r. By comparing this result with the expression for the energy U0, we can write the energy U of the capacitor with the dielectric between its plates as the energy U0 of the same capacitor with a vacuum or air between its plates, over the relative permittivity epsilon naught of the dielectric. Now we determine the difference between the potential energies U0 and U, which is equal to U0 minus U0 over epsilon r. Then the change in the energy of the capacitor can be written as the potential energy U0 of the capacitor with a vacuum or air between its plates, times 1 minus 1 over the relative permittivity epsilon r of the dielectric material. Here the multiplication factor of U0 is always positive since the relative permittivity is greater than 1 for any material, that is the energy of the capacitor is reduced by the dielectric slab inserted into the space between its plates. Hence, the difference in the potential energy represents the energy loss of the capacitor which is interpreted as follows. As the dielectric slab is introduced between the plates of the capacitor, the electric field inside the capacitor exerts an attractive force on the dielectric because the polarized material lowers the electrostatic energy of the system. If the slab moves inward without acceleration, this force performs mechanical work on the slab pulling the material inward. The decrease in the electrostatic energy stored in the capacitor is therefore converted into mechanical energy transferred to the dielectric. As the result shows, the greater the relative permittivity epsilon r of the dielectric, that is the greater the multiplication factor of U0 on the right-hand side of the equation, the greater the energy lost by the capacitor. Now we consider the second case where the voltage through the capacitor is kept constant while the dielectric material is inserted between the plates of the capacitor. Then the voltage V0 is constant, that is V0 of the capacitor without dielectric is equal to the voltage V of the capacitor with dielectric. The relationship between the capacitance still holds, that is the capacitance C is given by the relative permittivity epsilon naught of the dielectric, times the capacitance C0 of the capacitor without dielectric. In this case the potential energy U of the capacitor is still given by 1 over 2, times the capacitance C times the square of the voltage V. The substitution of the expression for the capacitance and the voltage into this equation gives 1 over 2, times epsilon r times C times the square of V0, or the relative permittivity epsilon r times the potential energy U naught. If we calculate the difference between the potential energy U and U naught, that is the difference between epsilon r times U naught and U naught, then we find that the change in the energy stored in the capacitor is equal to the potential energy U naught of the capacitor with a vacuum or air between its plates, times the relative permittivity epsilon r of the dielectric inserted between the plates minus 1. Here the multiplication factor of U naught is positive, showing that there is an increase in the energy stored by the capacitor. The energy gain produced in this way is supplied by a power source, for example a battery, that maintains a constant potential difference between the plates of the capacitor. Some amount of this supplied energy becomes additional electrostatic energy, while the rest is converted into mechanical work pulling the dielectric inward. As the result shows, the greater the relative permittivity epsilon r of the dielectric, that is the greater the multiplication factor of U naught on the right-hand side of the equation, the greater the energy gained by the capacitor. This effect indicates that a dielectric always tends to move into the region of stronger electric field because polarization lowers the energy of the system. Whether the energy stored by the capacitor decreases or increases depends on whether charge or voltage is constrained externally. The conversion of electrostatic energy into mechanical work in this way have many important practical implications in electronics and electrical engineering. Examples of the application of this effect include micro-electromechanical systems, electrostatic motors, precision pointing devices, and micro-switches.